Hey everyone, welcome back. This is lab number 9 in Embedded Systems. The objective of this lab is to use an ESP8266 Wi-Fi module, this tiny little guy that we're going to connect to our microcontroller board and nuclear board and use it to control the green LED on the board wirelessly to turn it on and off using a smartphone app. So ESP8266 module is understanding so-called AT instruction set. We're not going to spend time going through this, but we're going to connect the module using a USB to serial converter to the laptop and poke at it trying a couple of these AT commands. Alright, so let me switch the camera to the camera that I'll show you how exactly I'm gonna do that. So as you can see over here on the left hand side here, you'll see a schematic diagram that shows what this experimental setup in this first the experiment looks like. So the ESP8266 has a couple of pins. The ones that we need to connect as shown over here, the power, the VCC and the enable or CH_PD pins need to be connected to 3.3 volt that will get out of this USB to serial converter adapter that is connected to my laptop where I'm running a termite terminal, the one shown over here, and so that those are the VCC 3.3 volt. The ground, the blue line over here, is connected from the ground of the module to the ground of the converter. And then the RX of the RXD of the Wi-Fi module is connected to the TX of the adapter of the converter. Likewise, TXD shown over here is connected, of course, to the RXD of the converter. This little breadboard is only used here to be able to get two VCC to 3.3 volt connections to the ESP module. So as you can see over here, this is the USB to serial converter connected to my laptop. I'm getting out with the VDD VCC to this little breadboard. From where I'm forking the two wires that connect to the VCC and the enable pin. The other connections are the ground and the TX and RX. So here are a couple of AT commands that this module understands. For example, once that is connected and the termite terminal is connected with the right baud rate here as well. By default, these modules come set with a baud rate of 115/200, so we'll change it to 9600 later on, but before that I just wanted to show you some of the basic commands that you can once again see them in this instruction set manual. So for example, if you just say AT, if everything is okay, you would get back an OK. If you want to reset the module, you would say AT plus RST like that, and then the module gets reset. If you want to check the firmware type, then you would type here in the terminal the command AT plus GMR, and then you would see that the version of this particular Wi-Fi module that I'm playing now with is as of July 1st, 2016. The AT plus CW mode equals 3, sets it to be a both station and access point, just like that. If you want to query the local access points, you would say AT plus CW lap, list access points, and after a second or two you'll see here listed quite a few of those that are around. Now, in the actual lab example that you'll do later on, I'm asking you to use a baud rate to talk to this module over 9600. So you can use the command AT plus CIO baud and then pass it as a value 9600. So if you say that, now if you try to do anything else, the module will not be able to tell you anything because the baud rate just changed. So in order to be able to continue to talk to it, we'll go here and change to the baud rate that we just changed to 9600, and then if we continue to talk to it, then we'll see everything is okay. So we just changed the baud rate of the Wi-Fi module to be 9600, and this is how you're gonna use it within the example number one of this week. All right. So one more thing I wanted to show or mention. Well, it appears that it is not possible to change, at least with this version of this firmware for this particular Wi-Fi modules, the name. However, each of these Wi-Fi modules comes with a unique name that you can find out by going and typing the command AT plus CIFSR, and then you get a response. If you look there, you will see the last 6 digits of this ID address are gonna be the characters that you will see when you will scan with with another Wi-Fi device the name of your particular Wi-Fi module as listed with. So for example, if I go with my iPhone and I look at the Wi-Fi networks around, you will see over here that the AI Tinker underscore 23 Dept64 is the name of this particular Wi-Fi module, which has as the last 6 characters precisely this digits that you see over here in the termite terminal. So you do have your Wi-Fi module with a unique name, whose last 6 characters are the digits that you'll find by using this command. All right. So that's all I wanted to show you within this first part of this video. Next, we're gonna go and do the connections to the Nucleo board. So let's do that. All right, let's do the actual example number 1 from this lab. I have put together here a brief description of it. As you can see here on this slide, the Nucleo board is connected to my laptop, where we'll see the serial terminal within the STM32 IDE. The Wi-Fi module, the ESP8266, is connected to the Nucleo board, and it talks wirelessly via Wi-Fi to an Android app on an Android device. Let me switch my cameras and show you the experimental setup, which is shown over here. This is the Nucleo board. Of course, we have connected, as we've been doing already since a couple of labs back, the LCD display. Here is the Wi-Fi module that you already seen before, and this is an old used for this purpose only smartphone, one of my old phones. The connections for this experimental setup are shown in this slide over here. You'll see here in the middle the Nucleo board that needs to have connected to this LCD display using this connections as shown over here, from display to the Nucleo board, and the ESP8266 connections are as shown over here, and as listed on this in this little text box here as well. And you'll see here again that the VCC and the chip enable will see H_PD of the ESP module need both to be connected to 3.3 volt, which we do have available as two adjacent pins here on the Nucleo board. So let's see how this works. The idea is that the smartphone app is gonna send two separate commands that are basically one or two. I'm gonna generate those commands from within the smartphone app by pressing one of these two buttons, hard beeping or hard fading, and when I'm gonna press the first button, I'm gonna send a control of 1, and that will be received by the Wi-Fi module, and that will have as an effect the turning on of the LED on the board. If I press the second button, I'm gonna turn the LED off. So basically it is a remote control via Wi-Fi of the LED button on the board. So let's magnify this and turn on this phone. You'll see here already my app. If you look at the Wi-Fi connections, you'll see that the Wi-Fi module is connected. The app has these two buttons, and when I'm gonna press the first button, I should be sending a control command of 1 to turn the LED on the board. And I don't know if you just caught it, but it just turned on over here. If I press the other button, that will be sending a control command 2 that will tell the board to shut off the LED, and you see it's off. Alright, one more thing I wanted to show you is that when you use this app and turn on and off the LED on the board, at the same time the program sends these messages to the serial terminal of the STM Cube IDE as shown over here. For example, the LED is on or off. So just a little bit about the code. It's very simple, and I won't have time to go in order to keep this video rather short, but if you go to the top, I have quite a few comments that will help you navigate through. Essentially, if you look at the main program, you will see some initializations, including the SPI1 that helps us talk to the LCD display, as well as the UART1 that is connected to the Wi-Fi module. The LCD is initialized over here, and then the Wi-Fi ESP8266 init is called, which runs all of those AP commands that you've seen earlier, whose responses were shown in this serial terminal as you see over here. When I sent the I got the OK, and then I reset the module, and then I make it an access point, like this, and then a couple of other commands that you can see here after the main program at the bottom here, the listing of the 80 commands. Once that is done, then in the main program we basically get into the forever while loop, where we're reading from the Wi-Fi, and do the same thing every iteration of this while loop, essentially looking for the keywords effect equals 1 or 2, and if that next character after that effect equals is 1, then that's when we know we received the command 1 to turn on the LED on the board, and that's what we're doing over here. If the command that was received was a 2, then we will turn off the LED on the board. At the same time, we print all of those messages on the LCD display, as well as into the serial terminal here. If none of these two commands was received, 1 or 2 or something different, then that is the case of this else branch of the if statement, where we print on the LCD display that we received an invalid control, print that to the serial terminal as well, and that is pretty much it. The functions necessary to talk and work with this Wi-Fi module are shown over here. I will let you take a look at this code. It's rather simple and self-explanatory. We'll talk more in class as well. The entire source code of this project, as well as the entire source code of the Android phone app are available on the links included in the description of this video. So that is pretty much it. I hope you learned something, and I'll see you next time.